time to get prepared to learn about three extremely important functional groups, so acetals, amines, and enamines. We want to learn all about their formation and actually their destruction, aka hydrolysis. We'll get to that later. And we want to be able to know how to make them and when to use them in synthesis. But before we can even deal with that, we need to set the stage. So if you take a look at acetals, amines, and enamines, I've drawn generic functional groups here. You might notice why we are talking about these right now. So the starred carbon in all of these cases, I'm going to highlight it in yellow too, it came from a carbonyl carbon. How can I tell? Well, carbonyls have 2 bonds to oxygen, right? So does this carbon of the acetal. It has this bond to oxygen and this bond to oxygen. They're just 2 different oxygens. The amine, 2 bonds to nitrogen, which is like oxygen, right? And then finally the enamine, this kind of looks like an enol. And what do enols come from? You got it, carbonyls. So all of these are derived from carbonyls. To set the stage for our exploration of those very important functional groups, let's review a functional group that is slightly less important that we've discussed already in our initial discussions about nucleophilic additions to aldehydes and ketones. So we've learned that when we treat an aldehyde or a ketone under basic aqueous conditions, we will observe hydrate formation. Now typically, though not always, the aldehyde or ketone is favored at equilibrium. And that has to do with a strong CO double bond. Let's go ahead and draw the mechanism for the hydrate formation anyhow. We can see we formed 2 bonds. We formed a CO bond and an OH bond. Now we're in base, so we are probably not going to protonate something. We're not going to make the OH bond first. So let's go ahead and form the CO bond first. So the aldehyde, this is going to be an electrophile. This is an electrophile. The base hydroxide, it's going to be acting as a nucleophile here, and it's going to attack the carbonyl carbon. So we have a nucleophilic addition. And this step is reversible. All right, so we formed this intermediate. The stress on this intermediate is the negative charge on oxygen. It's relatively basic, so it can get a proton from the proton source. In base, the proton source is water. Okay. And proton source is a fancy word for acid. So in basic aqueous solution, water is going to be the proton source. All right, and that gets us to our hydrate. Excellent. Now if we change this up just a little bit, instead of using hydroxide, so on the previous slide we had hydroxide, let's use sodium methoxide instead. And then instead of water, we'll use methanol. So methanol is the conjugate acid of methoxide, just like water is the conjugate acid of hydroxide. So methoxide is either going to act as a base or it's going to act as a nucleophile. And methanol is probably just going to be a proton source. It's going to act as an acid. Even though it's not very acidic, in basic solution, it can act as an acid if we needed to, just like water can. Look at the product. We've made 2 bonds. Okay, so let's go ahead and make the carbon-oxygen bond first. So methoxide is going to donate its non-bonding electrons on oxygen to pi star CO of the carbonyl, and that's a nucleophilic addition step. Now we can see just like before, sorry this is ugly, just like before, the stress on the new molecule, the intermediate, is going to be the negative charge on what used to be the carbonyl oxygen. And so we're going to protonate that. And again, our proton source is methanol. So lone pair of oxygen accepts that proton from methanol. And we have our proton transfer step. And we get the hemiacetal. Now, I did not define hemiacetal. I apologize. Hemi means half, and a hemiacetal is simply half of an acetal. If you recall the acetal functional group from the introduction, the acetal functional group has two ether-looking, so two alcohols bonded to the same carbon, which used to be a carbonyl. For the hemiacetal here, we have one alcohol, so one little ether-looking group, and then one hydroxyl, one OH, bonded to the same carbon. So it's half of an acetal. It only has one of the OR groups, not both. And when you're in basic solution, the hemiacetal is where it stays. You might notice one more thing, that just like hydrate formation, the equilibrium constant for this reaction is less than 1. Now, however, this is pretty interesting. This is an example of an intramolecular hemiacetal formation. What? Okay, well, let's look at what's going on. So we definitely have a hemiacetal. So that carbon that I just put a star next to, it's making 2 bonds to 2 different oxygens. Okay, 1 each. This is the OR, and this is the OH. So it is a hemiacetal. And it does indeed come from an alcohol reacting with an aldehyde. Now on the previous page, it was an alkoxide. Well, we're going to get that by deprotonating this alcohol with the base in just a second. Okay, let me just tell you the fun fact about intramolecular hemiacetal formation. So when you have an alcohol and the aldehyde in the same molecule, it's going to make a ring. That's why it's called intramolecular. And the cyclic hemiacetal, typically these are actually favored at equilibrium. So the equilibrium constant for this reaction is greater than 1. So that's pretty cool. And we'll learn about why this is so important later in the semester. So you can see we have 2 bonds to form. We have this CO bond to form, and we have this OH bond to form. We're going to break the pi bond, so just the pi bond, and then we're going to break the OH bond. Let's number our carbons. So the carbonyl carbon, the acetal, hemiacetal carbon, I'll call that carbon 1. I'm just going to call this oxygen, I'm going to call it atom 5 because it makes a bond to the carbonyl carbon, carbon 1. So we're in base, so the first thing we're going to do is deprotonate something. So I'm going to go ahead and deprotonate the alcohol portion of this molecule. And that essentially accomplishes step 1, right? Which was to break this bond here. So we have a proton transfer reaction. Now we have a pretty good nucleophile. We have our electrophile. That's the aldehyde. So the oxygen, the alkoxide is going to close down on the aldehyde and make a 5-membered ring. So you'll remember that 5-membered rings are stable ring forms. They have very little ring strain. Go ahead and draw the 5-membered ring, then put your numbers in and go ahead and draw what substituents are supposed to be at each atom. That's our trick here. All right, so I know carbon 1 had been the carbonyl carbon. It still has 2 bonds to oxygen. So I should mention something really important here. If you're wondering, how are you keeping track of these carbons? The way I'm doing this is by understanding that oxidation state is not going to change. So because there's no oxidants or reductants here, it's just base. So carbon 1 has 2 bonds to oxygen always and forever. So even in the product, look, 2 bonds to oxygens. That's how I knew that was carbon 1. And here in this intermediate, it has 2 bonds to oxygen. carbon 4, carbon 4. It's only going to have one bond to oxygen, always and forever, because there's no oxidants or reductants in the reagents. So we're not going to be changing oxidation state. So that's how I can tell what the atoms are. And then when I do this key bond forming step, you just count between the two atoms that are making the bond, and that tells you the ring size. All right, let's go back to where we are. So we're right here. The stress on this molecule is the negative charge on oxygen, the alkoxide, and so it's going to get a proton from water. And I didn't explicitly say this was aqueous. It is, but also I did form a molecule of water in this first step here in case you were worried about it. All right, got it. Now you notice that I have a series of reversibility arrows, right? Reversible arrows. So each of these steps is reversible. It's a series of equilibria. And that means that hemiacetal formation can run in the forward direction, as I have written here, or it can run in the reverse reaction. And you want to be able to draw the mechanism for both of those scenarios. So here I have the reverse direction. So decomposing the hemiacetal to the aldehyde and the alcohol. So go ahead and pause and see if you can do this. It's going to be the exact reverse of the mechanism that we just drew. The exact reverse. All right, what can we see is happening? Well, I think we should number our carbons. So carbon 1, that's the carbonyl carbon. It has 2 bonds to oxygen, and oxidation states are not going to change. So I know that this is carbon 1 in the product. And then from there I can just number. I know that this bond was broken, right? There's no bond here between these guys in the product. I can see that this bond was made, and that this pi bond was made. And now this oxygen looks like this one, so I know that that OH bond was cleaved as well. So I just need to go ahead and do these things in the order that makes sense. Yeah, sounds easy, right? Right, well, we're in base, so we're going to deprotonate something. So I know that it's not really easy, but you have to reason through it. If you're in base, see if deprotonating something is reasonable. And in this case, it is. So we're going to deprotonate that oxygen. And if you go and look back at the reverse reaction, that was the last step, right? And the last step of hemiacetal formation, we protonated. So now going backwards, we're going to deprotonate. We're going to deprotonate. So that's what we're doing right now. Okay, now we've deprotonated. We know we need to break this bond here. We need to make this pi bond. We're going to do that now. So we're going to reform that pi bond, lone pair push. That's really the driving force for this reaction. So reform that CO pi bond. Break up that hemiacetal. So you break that ring. And then we're going to get an intermediate that looks like this. And I really like to draw it in the exact same shape, and then we can rotate bonds to represent reality. But it's just so we don't lose any atoms. All right, and now we do like to draw carbonyl or aldehydes with their hydrogens. So there it is. It was there the whole time. We just weren't showing it. All right, we are almost there. All we need to do is form the OH bond. Great. What is our proton source in basic aqueous solution? Correct, water. So get that proton from water, and we're done. I just want to point out, water is the proton source in basic aqueous solution. Okay, so practice this. Learn it forwards, backwards, upside down. All right, now that we have that little fun detour, I promise it's not really a detour, even though it feels like it is. It's getting us set up. Let's try to get to really framing the question at hand now. So in this discussion and in our previous class, especially chapter 17, looking at nucleophilic additions of aldehydes and ketones. So we've added some nucleophile, we've had some proton source. Our products have looked primarily like this. What we've noticed is the oxygen from the carbonyl has been retained, meaning it's still in the molecule here. All right, so why do you think that is? Well, if you said because hydroxide is not a leaving group, you would be correct. You guys know that we cannot do E2 of alcohols, and you know this looks a little bit like an alcohol. It's not exactly one, but it looks similar. This is a bad leaving group. Okay, so what was our solution for making oxygen a good leaving group? It was making it water. That's right. And how did we make it water? Well, we used an acid. Okay, so we used some sort of acid, and we've been under basic conditions so far. So now we're going to switch it up to acidic conditions, and we're going to see that we're going to form some entirely new functional group. I'm going to make it really weird and generic. And that oxygen of the carbonyl, it's going to totally leave. And it's going to leave as water, which is a good leaving group. Now, if you have no clue what I'm talking about right now, okay, that's fine. Come back and listen to this again and see if it makes a little more sense. So under basic conditions, typically that oxygen was retained, the carbonyl oxygen was retained. Under acidic conditions, we're going to see that we can make it leave. And we'll get a totally new functional group in water. We'll just peek at the basic conditions one more time so I can kind of show you. Let's look here. So at the hemiacetal formation, let's get some hot pink. This oxygen of the aldehyde, it is right here, retained, right? Still there. Hydrate formation. This oxygen is retained. We were saying it's that one. All right. So under basic conditions, that oxygen is retained. All right. So let's take a look at acidic conditions with an old friend, our old friend, the hydrate. As it turns out, when you subject an aldehyde or ketone to acidic aqueous conditions, you can also get the hydrate. How will this be different than aqueous conditions? You guessed it. You were going to protonate first. And in fact, as you may suspect, we're going to protonate the carbonyl oxygen using hydronium, or you can use the H+ shortcut, that's okay. When you protonate this aldehyde, you have made a really strong electrophile. It is going to undergo nucleophilic addition, and water is going to be that nucleophile. So only one around. Water is a weak nucleophile, but it's still a nucleophile, and the protonated carbonyl, it is a strong electrophile. Look at that positive formal charge on oxygen. Of course, I should just quickly mention, that positive formal charge is shared with carbon via this resonance structure. Okay, back on track. So we're going to have water attacking the protonated carbonyl. That's going to form the protonated hydrate. And now how do we get to the final hydrate? We just need to deprotonate. Our basic source in this aqueous acid is going to be water. So now water is acting as a base this time. So water acts as a base and acid, and an acid and base, yay. And now we get our product. All right, if you can't really reason through it the way that I just did, or you need another way to look at this, proposing this mechanism, look at what bonds are made, right? You know that you have to make this CO bond, and that's going to come from water. You know you have to protonate the second alcohol, and that's going to come from the acid source. So you can reason your way through this. No, if you recall the point that I was making the point that in aqueous acid, you can actually lose this oxygen altogether. And now some of you might be saying, but it's still there, it's right there. Maybe actually, not necessarily. So I probably should not explain this, but I'm going to do it anyway. Yay. All right, so let's look at that pink oxygen. Remember, all these steps are reversible. So what can happen? Well, that pink oxygen, it can grab a proton, it can deprotonate hydronium, and go right back to the protonated hydrate, right? But this time, it's the pink oxygen that got protonated. What can the protonated hydrate do? It can expel water. It can go backwards. It can go over here. Okay? And then what happened to that pink oxygen? It's gone now. We've lost it. Okay? So that might not be obvious when you look at the hydrate, but you may even lose the carbonyl oxygen in the hydrate. All right, now that I've thoroughly confused you, let's preview your assignment here. So learning about acetals, amines, and enamines. Now this is going to be unambiguous for you. So here's the carbonyl oxygen, and it is nowhere to be found in these functional groups. And in fact, it's left as water every single time. So that oxygen has left as water. Usually, actually, for these reactions in lab, you have to remove water. You have to dehydrate it in order to move the equilibrium to the products. But that's something you can worry about if you ever do these reactions in lab. And then what did I say that you have to have in order to generate water? You have to have acid. And in fact, for each of these reactions, you have acid. pH 5, I know that feels weird. It just means it's slightly acidic. All right, so you've mastered these nucleophilic additions in base. Now you're going to master them in acid. So study your assignment, and I'll see you in class.